So, we talked about graphs earlier. So, let us consider one aspect of graphs. This is called connectedness and a notion of distance. So, what is it that we can do when we have a graph? So, recall again, graph is just a sequence of vertices and edges. So, when I have such a collection of vertices and edges, what I can do is consider all possible paths or walks as they call on a graph. So, here is a graph with 6 vertices. I am just going to, so we always have labels on the vertices. So, these are 4, 5, 6 and these are the paths between these various vertices. Now, what I am going to do is imagine walking along this graph following the various paths. Okay. So, let us define a walk, define a walk on a graph is the following. It is just a sequence, it is a sequence which looks like the following. You start at a vertex, let us call it V0, write it here. So, it is a sequence, you start at a vertex, then you follow an edge. So, for example, if I start at vertex 4, there are 3 possible edges which go out of it, 3 paths. So, I follow one of them. So, from, let me call it E1. So, I follow an edge which leads out of V0 and ends at some other vertex V1. Then once I reach V1, I follow some edge which is leads me out of that next vertex, takes me to something else and so on, dot dot dot. So, here is a formal way of defining what a path is. So, it ends at EK, VK. So, a walk on a graph is just a sequence which looks like this, V0, E1, V1, E2. So, I can put commas if I want. So, here is my sequence such that all my VI's denote vertices, EI's denote edges, they belong to the edge set, and the ith edge EI is an edge connecting, is an edge between its 2 neighbors. So, for example, E1 connects V0 with V1. So, this is between Vi minus 1 and Vi. Okay, and this should be true for all I equals 1, 2, 3 till k. So, this definition of a walk is somewhat formal, but it correctly captures the various possibilities that we want to allow. For instance, a walk is allowed to traverse the same edge more than once. For instance, you could start at 4 and then go along this edge to 3, go to 2, then go back along this edge back to 3 and back to 4. So, that is a walk. That is allowed because after all a walk is just a sequence of vertices and then edges which lead out of that vertices to vertex to the next vertex. Okay. So, the other thing you could do is you may not retrace the very same path, the very same line, but you may revisit the same vertex more than once. So, that is also alright. So, for example, you may just go once around. So, start at 4, go to 3, 2, 1, 5 and come back to 4 and then go to 6. So, that is also allowed as a walk. So, the walk is really what it is, it is a walk, it is all possible, any such path which travels the various edges of the graph is called a walk. Okay. Now, let us define 2 other variations of this, or at least one other variation that will be useful. If the walk does not come back to the same vertex more than once, then we call it a path. So, let us define paths. So, definition, a path is a special kind of a walk. The graph G is a walk which does not revisit the same vertex more than once. So, it is a walk the way we wrote it, V1 etc. till ending at EK, VK. such that the VI's are all distinct, such that Vi is not equal to Vj for I not equal to j. Okay. In other words, the vertices that you arrive at are all distinct. So, that is what a path is. Okay. And that's one definition. The other definition we need is the notion of a length. So, this is the intuitive definition. If I give you a walk, the length of a walk is just the number of edges in the walk. So, the length of a walk is the number of edges in the walk. So, for instance, if you go back to that earlier graph we had, and if you look at the walk which goes from 4 to 3 back to 4 to 3 to 2 back to 2 and back to 4, this path or this walk has length 4. Okay. So, this is a length 4 walk, go back down, but this is not a path. Okay, it is a walk, but since you sort of revisit the same vertex more than once, for example, you come back to 3, you come back to 4, this is not a path. Okay. So, there is this subtle difference between walks and paths, but just to get a sense for how these definitions work, here is a sort of cute little fact, is also useful in certain contexts. So, let us call this a little lemma. So, it says that suppose you have a graph. So, and you take two vertices u, v in V, and among all possible walks between them, okay, consider all walks between u and V. So, the set of all possible walks is usually an infinite set. Why? Because imagine again, if in that earlier example you had to go from 4 to 3, well, it seems like there is only one obvious quick way of getting there, just take this one edge and go from 4 to 3, but there are actually infinitely many walks which will go from 4 to 3. Well, for example, you could do the following: you go from 4 to 3, then you go back to 4 and then back to 3, right. Now, you could keep doing this sort of oscillation many times. So, if I call this edge as E, then I start at 4 and then go along this edge to 3. This is one walk. Or I start at vertex 4, edge to 3, I go back along the edge to 4 and come back along that edge to 3. So, here is another walk from 4 to 3 and so on, right. So, I can keep oscillating back and forth and keep reaching 3 in very many ways. So, the number of walks between u and v will usually be an infinite set. Okay. So, consider all walks between u and v, and among those walks, let us find a walk of the shortest possible length. Okay. So, let us call it something, let pi be a walk of shortest possible length. Okay. Now, notice that such a walk will always exist. So, even though the total number of walks is the set of all walks is infinite, when you write all possible walks down, okay. So, here again there may be many other walks, you could go from there to 2, and then go back to 3, or you make one full circle around that pentagon and go back to 3 and so on. Among all possible paths, you will be able to find at least one path, then sometimes maybe more than one path, but you will be able to find one path of least possible length. In this case, what is the smallest length to go from 4 to 3? Well, it is just length 1. You just travel along E and you can reach from 4 to 3, and that is the smallest possible length you can have among all possible paths. Okay. So, in this example, okay. So, before I state the lemma, so here these are all just some preliminary, we will come back to state the lemma. So, here is some preliminaries about what shortest paths look like, etc. So, example, from 4 to 3 in this graph, there is only one shortest path, and that path just takes the edge E. So, goes from 4 to 3 using the edge E. Now, there could be instances where there is more than one shortest path. For example, if you look at this graph here, just the square, the cycle. Now, how do you go from 1 to 3? Well, there are again infinitely many ways, infinitely many paths going from 1 to 3, but there are two shortest ones. Okay. What are they? One of them is to go from 1 to 2 to 3, the other one is to go down to 4 and then go to 3. So, here are two shortest paths, they both have length 2, but the point here is that you will always be able to find at least one path of the shortest possible length, because the length is some natural number and you cannot have, there has got to be some smallest number, some smallest length. Okay. Now, this particular quantity is a very useful and important thing which comes up a lot. So, let us first define that. So, definition: given 2 points in the graph, given 2 vertices, given u and v in the vertex set of a graph, we define the distance between them. So, this is called distance between u and v, or duv, as follows. You take all walks, it is the minimum of the length of pi, used length of pi, where pi is a walk in the graph connecting u and v. Okay, so among all possible walks, you find what are the lengths and take the minimum of those lengths. That minimum is called the distance between u and v. Okay, so this is only possible, of course, if you can find at least one walk which connects u and v. Sometimes that will not be possible. For example, if I have a graph like this, the same cycle graph, and maybe these 2 points sort of are separate. So, I have got 6 points in my graph, but 5 and 6 cannot be connected by an edge, are not connected by edges to 1, 2, 3 and 4. So, in this case, you cannot go from 1 to 5 using, there are no walks which will take you from vertex 1 to vertex 5. Okay. So, in that case, we just define. So, since there are no paths, in that case, so it is equal to this or infinity. So, if there are no walks, u and v, in that case we define the distance to be infinity. Okay, just some formal, think of infinity as just some symbol here. In all other cases, it is some finite number. Okay, it is a minimum of the lengths of all possible walks. Okay, now the key thing here to note is that this is not distance in the usual sense of the word. Again, like I mentioned once earlier, we are not trying to think of these as 4 cities and connected by roads, and the length of the distance between the city 1 and city 2 is not the length of the edge between them and so on. So, we are not thinking of distance in the usual sense of distance. Here distance just means the length of the walk, which means just the number of edges that are there. Okay. So, if you think back on the example of trains that we had given earlier. So, let us go back here. So, here the question is, suppose this is my graph and I want to go from let us say where to where, I want to go from 6 to 1 for instance. Okay. And when I say the distance, so what is the distance from 6 to 1? This is just, I look at all possible walks and try to find the minimum length among them. So, here is one, this guy has length 3. Now, I could also try the other one, which is I go to 4 and up to 3 to 2 to 1. So, this is 1, 2, 3, 4 in this case, right. So, the pink path actually has greater length, length 4. Now, if you thought of this as connection, so the distance is 3 here, not 4. If you thought of each edge as representing a single direct train, this is like saying what is the least number of direct trains I can take to go from 6 to 1. So, that is my distance, notion of distance here, the number of trains I need to take. It is not the actual physical distance or in kilometers, for example, between cities. Okay, so I hope that that notion is clear here. This is just counting number of edges between them. Okay, so now here is our little lemma. If you take a minimum length walk between 2 points, if pi is a walk from 2 vertices from u to v, and suppose this is a minimum length and length of pi is the minimum of all possibilities. In other words, this is what we call the distance, right. If length of pi equals the distance between those points, meaning it is the minimum, then pi is not just a walk, it is actually a path. So, I am assuming u and v are some 2 distinct points. So, I take 2 distinct vertices in my graph and I join them by a path of least length. Then I claim that this is by a walk of least length. Then the walk is in fact not a walk, but rather a path. Okay. So, let's see what the proof involves. So, this is a nice little thing which tells us how paths and walks differ. So, the point here is that I am starting at u and I am ending at v, and somehow I am getting from one to the other by using the smallest number of steps, right, the least number of edges. That is what pi being minimal will tell us, the length being minimal. So, I have drawn a picture of the path pi, the walk pi. Now, pi is a path is like saying there are no, you never revisit the same vertex again, right. So, you do not come back to the same vertex again. Now, how can this be, suppose not, suppose this did not happen. Suppose pi came back to the same vertex. So, what do I mean? Maybe pi was like this, okay, then came back to this vertex and then from there it proceeded again and reached v. Suppose this was my path pi. Okay. Now, what I have drawn here is not a path, it is a walk because it has come back to a certain vertex again. Now, we claim that if this happens, then we can construct a shorter path than pi. Pi could not have been the shortest possible path between u and v. Okay. So, if pi is not a path, then we can construct, let us call it pi prime, a shorter walk than pi between the points u and v. So, this is what we claim. So, this is what we will prove. Okay. If pi is a walk which is not a path, then you can actually construct something shorter than pi. Okay. How do we do it? Well, the picture sort of tells you what to do. So, there is a certain portion of pi where you sort of do something wasteful, you sort of go around and then you come back to where you were earlier, right. Now, how would you construct something shorter than pi? You would just subtract out or you just delete that portion of the path. So, here is going to be our pi prime. We just take pi and delete the part of the path which comes back to this. So, just look at this and call this new thing as pi prime, and when you do that, so if you call this new path as pi prime, then it is clear that the length of pi is smaller than the length of pi prime is smaller than the length of pi. Okay. So, that is the basic idea. So, let us just write it out a little bit formally in this case. So, we assume pi is a walk, but not a path. So, let us write pi in that notation that we wrote out. vertex V0. So, V0 is actually U, and then there is E1 Vk. So, let me use V0 again, but V0 is U and Vk is V, okay, and U is not equal to V. Now, what does it mean to say it is not a walk? It is not a path, pi is not a path. Then it means there exists I not equal to j. So, let us say I less than j, such that the vertex Vi equals the vertex Vj. Okay. So, I and j are some numbers between 0 and k. Now, let us define pi prime as follows. Take the same as pi until you reach Vi, okay. But then from Vi to Vj is the wasteful part of the path. From that point on, we will just go along Ej plus 1, Ej plus 2 and so on till reach Vk. So, this is the path that I have cut and stuck back. Okay. Now, observe this is also a walk. Joining U and V, and why is it a walk? Because Ej plus 1 should be an edge joining Vi and Vj plus 1, but it is that because Vi coincides with Vj, right. So, to start with, Ej plus 1 was connecting Vj with Vj plus 1, but Vi and Vj are the same. So, this still connects Vi with Vj plus 1. After cutting, it still satisfies my definition of a walk. So, here is another walk which connects them, but now the key point that the length of pi prime is definitely strictly smaller than the length of pi, because the length is supposed to be the number of edges that I used. So, if you look at the original number of edges, there were k of them, E1, E2, Ek. For pi prime, what have I lost? I have gotten rid of all edges from Ei plus 1 to j. So, this is I have gotten rid of j minus I edges. So, from k minus j minus I, okay, and j minus I is strictly positive. So, it tells you that length of pi prime is strictly smaller, and that is your contradiction. So, we have basically proved this by contradiction. We assumed that pi was a walk which is not a path. That was our assumption.